special multiplication rule. All right, so yesterday we checked independent events by saying the probability of A given B is equal to the probability of A. Okay, what happens to the general multiplication rule in the special case where A and B are independent? So when they were not independent, right, we were doing and, A and B, we multiplied the probability of A times the probability of B given A, like those tree diagrams, right? When we were talking about Federer, we multiplied when he won, and then given that he won the serve, if he won the point, right? So there had to be that conditional probability for the second one, because the first thing depended on the second thing. But if they're independent, it's an even easier formula, all right? So if they're independent, which we learned this formula yesterday, this proves independence. Probability of B given A is equal to probability of B. Same formula we learned yesterday, just they switched the variable around, okay? So if that's true, you don't have to have the conditional probability here. You can just multiply the events together. No conditional probability on the second one, because we just said that this is equal to this if they are independent events. All right, so let's try a problem. The Challenger disaster. On January 28, 1986, Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was 0.977. But there were 6 of these O-rings, and all 6 of them had to function properly for the shuttle to launch safely. So assuming the O-ring joints succeed or fail independently, find the probability that the shuttle would launch safely under similar conditions. So we want to know the probability that it would launch safely. So in order for it to launch safely, we'd have the probability of every single O-ring to pass, right? So they've got the joints in there. So we've got joint 1 has to be okay, right? That has to pass. And the next joint has to be okay. So we'll say joint 2. And the next one, right? Joint 3 is okay. All the way up to joint 6. Okay, there are 6 of them. They all have to be okay. So what's the probability that one of them passes? Okay, this number right here. So a 97.7 chance that that one passes. But there are 6 of them. 2, 3, 4, 5, whoops, 6. Okay. Multiply those all together, and we get 0.87. So what does that mean? There was actually only an 87% chance that it would succeed because they all had to work. Since then, they have done updates on these. So the chances are a little better. Makes sense. Okay. How about HIV testing? So finding the probability of at least 1. Anytime you guys find the probability of at least 1, you should do it like this. Okay? The probability of at least 1 is equal to 1 minus the probability of none. So let's try that in this problem. Many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the test results. So clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, use of rapid tests increased the percent of clients who learn their test results from 69% to 99.7%. So that's good. But the trade-off for the fast results is that rapid tests are less accurate than slower laboratory tests. So applied to people who have no HIV antibodies, one rapid test has the probability of about 0.004 of producing a false positive. That is, of falsely indicating that antibodies are present. Okay, false positives are bad. They don't have HIV, but they're getting a positive test result. So that would be unfortunate news, okay? If a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the chance that at least one false positive will occur? So 200 people who don't have HIV, but what's the probability we actually get a false positive on at least one of those? Okay, so the probability of at least one positive test result is equal to 1 minus the probability of no positive test results. So the probability of no positive test results. Well, this right here, 0.004, represents getting a false positive. So that means that 0.996, that's what we want, okay? So we are going to do no positive test result, 0.996, and this has to happen 200 times. So each one, 0.996, 0.996, 0.996, okay? 200 times. So we do that and we get 1 minus 0.4486, which gives us 0.551. So there's actually a 55% chance that we're going to get at least one false positive when 200 people come in that don't have HIV. So that's actually pretty good chances, which is kind of sad, but that's because of the error that can happen, okay? So anytime you guys are doing at least one, it's easier to do 1 minus the probability of none. Okay, side note, this kind of ties it together here. We've got the multiplication rule. The probability of A and B is equal to the probability of A times the probability of B, right? This is only true if the events are independent, okay? Can we multiply one thing times the next thing? They have to be independent. Otherwise, you got to use that conditional probability second. Same with the addition rule. For the addition rule, just A or B, we add the events together. That only works when it's mutually exclusive, right? If it's not mutually exclusive, you have to subtract the overlap. So make sure you don't always follow those rules, that you pay attention to whether you have independent events or mutually exclusive events, or otherwise you use the other formulas. Make sense? Okay. So is there a connection between mutually exclusive and independent? Let's start with a new chance process. Choose a U.S. adult at random. Define the event A, the person is male, and the event B, the person is pregnant. It's fairly clear that these two events are mutually exclusive, right? If you are male, you cannot be pregnant. So what about independence? I know, all things are possible. Okay, anyways, we don't have to get into that. So what about independence? So you guys, if you know that event A has occurred, does that change the probability that event B happens? Yes, it does. If we know that someone is male, okay, then do we know that the person's chance of being pregnant is 0? Yes, okay? Because one thing does affect the other thing, right? It does affect the other thing. These are not independent events. So two mutually exclusive events can never be independent. And that's something you might want to write down, okay? Because if one thing happens, the other is guaranteed not to happen. So if they're mutually exclusive, then they are not independent. Yes, Jake. So you guys are going to try a couple problems. During World War II, the British found that the probability that a bomber is lost through enemy action on a mission over occupied Europe was 0.05. Assuming that missions are independent, find the probability that a bomber returns safely from 20 missions. Now they're switching it on you, right? Because they're saying this is the chances that they don't return safely. So what's the probability they return safely from 20 missions? So see if you guys can get that answer. Might need a calculator. So with 20 missions, so let's see if you guys got this right. So return safely is 95%. You have to do that 20 times. So to the 20th power, 0.3585. So that's kind of crazy. Even though it seems like small chances you don't return home safely, if you do it 20 times, that's a little scary. Only a 35% chance you return home safely. All right. Government data shows that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Because 0.08 times 0.3 is 0.024, can we conclude that about 2.4% of adults are college students 55 or older? Why or why not? Okay, not independent. Because you can have someone who's both, right? So being a college student, being 55 or older are not independent events.